Hi, this is Jason McIntosh. I'm going to show you how to use the MAE100 flow impedance apparatus to measure the impedance through a thin sheet of porous acoustic material. Over here we have the system. This is a prototype apparatus of the 100 that was built some time ago. I'm using some condenser microphones that use a constant current power supply shown here. Then I have the MAE206 amplifier here that's being used to condition them a little further. Make sure we got good signal to noise ratio into the data acquisition sound card that's used. The material that we're going to measure is shown here. This is a thin sheet of woven material. Here I've used a sample cutter to cut a 1-inch diameter sample out of it. This is going to go into the sample holder. There's a couple different types of sample holders, but generally it's going to be a 1-inch diameter disc. This one has a inner support where the sound is only allowed to pass through a 1 centimeter diameter area of our material. And to hold that in place, I have a little washer here. Normally I would take a piece of putty and putty around the perimeter of the washer to provide some extra compression and make sure that that washer doesn't move around during the measurement. But this acoustic material is pretty light. Just the weight and mass of that washer will hold it in place nicely. But if I had a little different material, a little thicker material, I'd want to use the putty. Now part of the measurement is to measure the impedance of the sample holder. Now I've already done that, so I'm not gonna repeat it here, but I'd measure the impedance of just this without the material, and then that impedance would be subtracted from the impedance with the material present, and we would get the impedance of just the material alone. But I've already, like I said, I've already done that. This is part of the MAE100. This is a low frequency, high intensity driver. This is mostly used for doing nonlinear measurements. This is a little speaker driver for doing broadband or high frequency measurements. Since we're doing low intensity measurements, I'm just going to use this for all the frequencies. And the initial stack up that Aries will ask for is going to be with this stack up here, so I'm going to put it in place so we can do the first measurement and not have to change the setup here. So back on Aries, I'm going to create a new flow impedance measurement module. Sound card's already been calibrated. I've already gone through and done the setup for this. I'm using a DP test apparatus for the apparatus to use. There's a number of apparatuses that can be chosen. Nexus is available if you've got one. Otherwise, you can use the MAE206, substantially cheaper. There's a microphone calibration that has to be done. This is covered in the manual. Some additional parameters. Here's the sample holder impedance that was measured. This is what's going to get subtracted from the actual measurement. And then the actual measurement is done under sample impedance. I've already got the sample diameter set to 10 millimeters. The sample thickness is only important if you want to normalize by thickness. We're not going to do that, so I'm just going to leave it as 1, an arbitrary number. We're going to measure from 50 hertz to 5 kilohertz. The MAE100 goes up to about 5 kilohertz. There's a higher frequency version of it, the MAE101, which goes up to about 12 kilohertz. We're going to do 100 frequency points, and I'm going to just do a log spacing. This parameter allows you to set the particle velocity through the material that's tried to be achieved during the measurement. By keeping this relatively low, substantially under about 1 meter per second, you ensure that you're measuring linear parameters and not getting any nonlinearities involved in the measurement. And we're going to go ahead and subtract the original sample holder. So I'm just going to leave this as the default name of dataset 1 and start the measurement. It asks you configure the system with the following stack up. We've already done this. So I'm going to hit OK, and this is going to take a few minutes to run, so I'll probably just skip through this in the video that gets posted. Okay, so it's done the low frequency measurements with the large stack up. Now it's asking us to switch it to just the 20 millimeter spacer. So I'm going to go ahead and change the stack up to just use the 20 millimeter spacer. We'll do the high frequencies. I'll go ahead and hit OK. Okay, so the measurement is done. I'll hit OK here. So looking at the impedance, we see that there's some frequency dependence to the impedance. We'll discuss what this means in a little bit here. So I'm going to go to the plotting section. I'm going to plot that data set that we just took. And I'm going to also go ahead and plot the sample holder impedance. I'm going to increase the line thicknesses here so we can see it a little better. So the impedance that we measured is in blue. The green impedance is the impedance of the sample holder itself. So the sample holder has very little real part to it. The imaginary part is dashed. The sample holder impedance has quite a bit of mass reactance to it. This is roughly j omega going up. Had we included this impedance with the actual measurement, this imaginary impedance would be way up here, and it would mostly be consisting of the mass reactance of the sample holder and not representative of the material itself. So it is important to subtract the sample holder impedance in most cases. So here's just the sample impedance. A few things to point out here is that it's non-uniform over frequency. If the material was held stationary, completely still, it is a porous material, so air can flow through it, and you'd experience the resistance of the air flowing through the material. If it was just if the material was purely stationary, we'd see that the real part was largely a constant value, independent of frequency, and the imaginary part would have a very little bit of mass reactance of the air inside the pores of the material. So it'd be a pretty boring plot if the material didn't move. But because the material is being placed in motion, we get this nice complex behavior here, and it bears some effort to understand this a little bit. So what we basically have is a parallel combination of the resistance of the air flowing through the material and the impedance of the material in motion itself. Now it's the parallel combination of this, so the net impedance will be less than either of those two impedances. So if I go ahead and I plot this in MKS rails, so I have rails up here, it looks like it's going to about 250 rails. The impedance can never be more than 250 rails because that's one of our two parallel impedances. So the impedance of the material moving causes the impedance to drop under 250 rails, and we get this complex behavior. Right here, there's an impedance minimum. We can see that if we plot magnitude. I'm going to go ahead and plot magnitude in dB. And you can see that we have a minimum at this point where the imaginary part passes through 0. This is the first drum mode of the circular disk sample that we have. At low frequencies, if this was behaving as a perfect membrane, we'd expect this to go off to negative infinity, the imaginary part, but that imaginary part is going back to 0, and that's because of the parallel resistance term that allows the air to pass through the material itself. At higher frequencies, we get into other higher order mode effects, which is coloring the impedance behavior. Then at the highest frequencies, those modes get so dense, there's so many modes per hertz that it just kind of gets all smoothed out to a nice simple behavior at the highest frequencies. So that's how this material is behaving. If you use this material in an acoustic application, it's worth understanding how its impedance behaves so that you can understand your design better. Now, one way to use this is to import this impedance directly into an Aries model. So I'm going to go to File, Clipboards. There's only one data set here. I'm going to select Save the Sample Impedance. Hit Save. I'm going to overwrite my existing data set that I made. And now I'm going to open up Aries model that I have previously built that shows a speaker radiating into free space, and we're measuring the pressure at about a foot away. Here in the model, I've got this resistance element put in here. We're going to use that momentarily, but for now I have the resistance set to 0, so this isn't doing anything to us. And the graph response is just showing this a classic speaker, classic baffled speaker response. Now I'm going to copy this into buffer A of this graph element and plot it. I think I need to set the line weight to be a little thicker. So now I've got buffer A is equal to the current buffer, so they're just lying right on top of each other. If I come in here and I use this feature to load the impedance of this impedance file that we exported, this option becomes available to use the file impedance data. I'm going to check that. I'm going to recalculate, and so now we're seeing the effects. The blue curve is the effect of having the material in place. Its main effect is to drop the response at resonance, so we're adding some damping, bringing that down. We don't see a lot of effect due to the complex frequency response of the material, but you can see we're getting a little bit of an effect in here. So all of those impedance variations of the material are causing just a few dB ripple in the response. Probably not important for most applications. But the main thing it's adding is this resistance that's dropping the response at resonance. So I'm going to go ahead and copy this into buffer B. I'll plot it and I'll call this with material. And now I just want to see, for the heck of it, what would happen if I didn't use the impedance of the material, but I just used a simple resistor. How well does a simple resistor model the behavior of the material? In acoustic terms, in acoustic ohms, 1 mega ohm is about kind of a little bit of resistance to add. So I'm going to add 1 mega ohm to this model, hit calculate, go back to my graph. So with materials in red, no materials green, and our 1 mega ohm is in blue. So it definitely increased, definitely had an impact. It decreased the response in resonance, but it needs to come down a little bit more. I'm going to go ahead and change this to 1.5. I did this previously. I think that worked the best. So I'm going to hit recalculate. And 1.5 is close. Looks like we got to come up a little bit more. I'm going to try 1.8. Close again. I guess I'll go to a full 2 mega ohms. Let's go to, I suppose, 2.3. I'll just quit there. So we're getting a fairly good match with 2.3 mega ohms to bring the resonant passband down. But if we zoom in here, it's not fully capturing the motional behavior of the material, but it's pretty darn close. So again, so these tools are meant to help you understand how the material behaves, to be able to measure its acoustical impedance, see how much of the material motion is affecting it, measure the resistance of the material, the DC resistance of the material, and then by using it in conjunction with the modeler, you're able to see what kind of impact you can expect that impedance to have on your overall system response. So I hope you found this useful. Thank you for your time.